type them in. What I thought of doing today is going over carboxylic acids. We sort of touched on it last time, but it was a bit of a rush. So we'll go over that, we'll go over polymerization and reaction schemes as well. And then we're done. Okay, so do you all recognize this as the carboxylic acid functional group? The C double bond oxygen, where the C is also bonded to an OH. Okay, do you all know that? So a yes or no? Great. Okay. Now, carboxylic acids can undergo different types of reactions. This one over here, where the carbonyl-carbon is very electropositive, you will look at that next year in level 3 chemistry. So we're not going to look at all the reactions where a nucleophile, something that likes something positive, comes in here and kicks out the OH. You'll do those next year. What you will be doing this year is looking at carboxylic acids as acids. So what do you know, how do we define an acid? Now this is going back to level 1 unless you've done the 2060 series. Do you know how, if I said what is an acid? Would you know how to define it? Nope. Okay. It's one that gives off an H+, which is really a proton. So we define it as a proton donor. Because if you think of a hydrogen atom has got one proton and one electron in it. That's all it is. So if I remove the electron to make it positive, all I've got is a proton. So we can say an acid is a proton donor. And it'll give off H+ ions. What are properties of acids? How would I know I've got an acid? How would I test to know the substance is an acid? Litmus paper. And more particular, what color change would I get? So if I used red litmus paper, would I get a color change? No, because the way I always remember it is whatever the color ends in, that's what the change must end in. So red ends in D, and acid ends in D, so it's got to change from blue to red. Red must be at the end because the D is at the end and acid ends with a D. So red to blue is alkaline, blue ends in E and alkaline ends in E, and blue to red is acid because both of those end in a D. Okay. There are also other reactions that you know, so you can do litmus or universal indicator, any of those indicators, okay, or you could test for pH in another way, like pH meter. So what number would it be sort of up to? Is it going, would something that has a pH of 6 be acidic? Any idea? Yes, it would. Correct. Okay, so anything up to just below 7 is acidic. If it's 6, it's not very strongly acidic at all. If it's 0, it's very strongly acidic. Okay, it's got lots of hydrogen ions present. If it's 6 or 6.5, there's only a few hydrogen ions present. 7 means it's neutral, so there are equal number of hydrogen ions to hydroxide ions. So 7 doesn't mean that there are no hydrogen ions present. It just means that any hydrogen ions are balanced by hydroxide ions in the solution. And then basic means I've got more hydroxide ions, so fewer hydrogen ions. So I've got only very teeny amount of hydrogen ions if my pH is, say, 11, but I'll have lots of hydroxide ions. So anything you learn about acids and bases can pretty much be applied to carboxylic acids. So don't compartmentalize your chemistry learning. Don't say this is organic chemistry, so I don't have to know anything about bonding or anything about acids and bases or anything like that. Always try and bring in and relate all your chemistry. Anyway, enough me talking. So you don't worry about the substitution that you get next year. Okay, and the one you have to think about this year is this acid-base reaction, where the OH bond breaks and you get H plus coming off. So the O keeps the 2 electrons, so you get C double bond O, O minus. So it's a COO minus anion, it's a carboxylate anion. Have you seen, like for instance, sodium ethanoate? Have you heard of that chemical before? Nobody? Okay. Who has ever added vinegar to baking soda and made a volcano? You know, added a bit of red food coloring to make lava and so on. Yep. So what happens there is we've got baking soda, which is a carbonate, hydrogen carbonate, sodium hydrogen carbonate, and we're reacting it with ethanoic acid. So it's a carboxylic acid where this is a methyl group. So I've got a carbon there, so that's ethanoic acid. And I get an acid-base reaction to form a salt and water and carbon dioxide because I'm reacting it with a carbonate. So forget about that top up bit up there. I'm going to flick through that. This is the one I wanted. So here's my ammonia molecule. So the ammonia will react because it's got a lone pair of electrons, and it'll take off this hydrogen ion as H plus. Okay, so that ammonia there is this one over here. And this is my carboxylate anion. It's got a negative charge. And my ammonium ion, can you see it's NH4 plus. So this is all negative, and that's positive. That's a straightforward acid-base reaction. Which functional groups, or which group of compounds in organic chemistry are basic? So carboxylic acids are acidic. Do you remember which ones are basic? So I'll just go through them and you can type down which one you think it is. Alkane, alkene, alkyne, haloalkane, alcohol, amine, carboxylic acid. Those are the 7 you have to know. So one of those is basic. Amine. Well done. Okay. So I could react any carboxylic acid with any amine. Okay, I made ammonia here, but that's not an amine because I don't have a carbon attached to it. But it undergoes the same sort of reaction. I'll get whatever the amine is forming the cation, and the carboxylic acid forming the anion. Okay, so here's an example of a test using sodium carbonate for the carboxylic acids. So, sorry, it's just got to crank up. And glacial ethanoic acid is just simply the very undiluted one. So if you've got this over here, that's the carbonate that they're going to add. It's a white powder. You know, baking soda or even washing soda, it's a white powder. So they're going to add that, and I'm going to just move it up. Okay, they're going to put it in now. And you should see, can you see that fizzing that's over there? Unfortunately, the clamp is sort of just where it's happening. So it's not very clear, but it's sort of gone opaque because there's lots of fizzing going on. And that test was carbon dioxide giving off, because did you notice how the flame immediately just went out? So the flame immediately goes out, meaning it doesn't support combustion, so it's a test for carbon dioxide as well. What is a better test for carbon dioxide when we want to check if the gas given off is carbon dioxide? Does anybody remember from last year? Level 1? Lime water. Well done. If lime water goes milky. So here they're doing, and so here they're going to also collect now. So carbon dioxide gas is heavier than air, so it's coming up in here, instead of just going and dissipating up there, it's heavier, so it'll actually try and fall straight down. So he's collecting the gas being given off, and let's move it on a bit. Okay, there's the lime water, and he's going to pour the lime water in, and it should go milky. So it was a colourless lime water, and when he's finished, can you see it's milky? So any carboxylic acid can react with a carbonate to give off carbon dioxide gas. Okay, so this is a way you could differentiate between if you were given an alcohol and a carboxylic acid. The alcohol wouldn't react to do anything with the baking soda, but the carboxylic acid would. Okay, now we've gone through then pretty much all the reactions, and here they all are. So as I say, there are quite a few, but you will, if you learn a bit at a time, you will get them in your head. The only one we haven't done is this one, which is polymerization. So notice alkenes tend to be all addition reactions. So I've done the blue over here is addition. So because I'm adding to the double bond, so I can form an alkane with hydrogen gas and platinum as a catalyst. I can polymerize, and we'll do that later. I can test for it, because remember when it decolorizes the brown bromine to form this colorless haloalkane, that's a test. I can do another test using purple permanganate, and so you can see I've got it blue and purple. Purple is oxidation, so it is an addition reaction and it's also an oxidation reaction. And I think in the exams they accept both, because it is both. You are like adding oxygen, you are oxidizing it, and you know permanganate, if you've done the 2.7 redox, you know it's a very good oxidizing agent. And here's the other addition one, which is adding water, which is H2O and conch sulfuric acid. Okay, who remembers Markovnikov? What is that? I don't mind if you quickly just type in the memory aid, but of course remember in the exam, don't give the memory aid, because they're not going to mark it. The rich get richer. Okay, good. So when we're adding to here, you look for the carbon that has the most number of hydrogens. That's not a hydrogen, so this carbon's only got one. This carbon's got two, so the hydrogen adds to the carbon that's got the most. That'll be the major product. You will, of course, get some of the other where the hydrogen adds on here, but not as much. Okay. Then we had, for both the haloalkanes and the alcohols, we could form alkenes. So you'll notice those are in red. They are the elimination reaction. So where we're removing two adjacent groups. Okay, so here's an OH and an H, or a BR and an H, or it could be a BR and a BR, although you haven't learned that yet. You've only learned the BR and an H. So look at the conditions. I'm using concentrated, okay, conch. So, and it's, what I haven't actually got on here, it's heated normally as well. They tend to be heated, you know, a lot more than the other ways. So we've got to drive the reaction to an elimination. We use Zaitsev's rule to work out which one is the one that'll be the major product that we'll get the most of, and what's the memory aid to remember that one? The poor get poorer. Great, because using that memory aid will make you also remember, poor gets poorer, there must be elimination because you're getting poorer, so you're losing something, so it must be an elimination. So if you have a look here, because the OH was on this carbon, the hydrogen the carbon with the most, let me get this right, if I go that way, we don't know what R is, so we can't really say, but we would have lost this OH plus either one of these hydrogens or that one, depending on what that R is. I don't know, but this will be one of the products, either the major or the minor. It all depends what this R is. So always look carefully at what you're given. This is just a generic to help you remember. Okay, and then the same thing here if I use a very strong base to try and drag off this HBr, because HBr is acidic, and if I use a strong base it'll drag it off. Okay, and I'm left with an alkene. Then we have the substitution reactions, haloalkane to alcohol, alcohol to haloalkane, haloalkane to amine, okay, and then also the alkane to a haloalkane. So it's Br2 with UV light or chlorine with UV light. The UV also acts as a catalyst, because remember I said alkanes aren't very reactive. Alkanes tend to just burn and not do much more, but you can react it with bromine and chlorine under UV light. There is also the alkynes. The alkynes do pretty much what the alkenes do, because you're just adding on, but you're adding on double. So you can add hydrogen to form the alkane, you can add hydrogen to form an alkene, or you could even test for it. You can oxidize it as well. Okay. Then what we did last time with the amines, remember it acts as a base, so I can react it with any acid. So notice HBr can come up in a number of places. There's HBr over here. I could use HCl. I could use ethanoic acid, you know, like that. Any acid. HBr comes up over there. So HCl I could have used if I wanted to make a chlorinated compound. So notice here for this reaction, I've got a number of substances I can use. As I say, I don't like using the conc HCl. I prefer only using conc HCl. The conc HCls to add onto an alkene, but to go from this, the haloalkane to an alcohol. I don't really like using the conc HCl, but I don't think it'll get marked wrong, but it's not the best one. Use SOCl2. I always recommend that one. Okay, so this just acts as a base, which means, can you see the amine, the NH2 has protonated, and then there's my salt formed, and my carboxylic acid does the same thing. It reacts now, because it's an acid, reacts with a base, sodium hydroxide, potassium hydroxide, and amine, any base, okay, to form salt and water. And of course, if it reacts with any carbonate, sodium hydrogen carbonate, sodium carbonate, potassium carbonate, it's going to form salt, water, and carbon dioxide. So those reactions you learned in 90944, you do it again here. Then the last one is the oxidation. You only have oxidation appearing really twice in your scheme. So when I oxidize an alcohol to a carboxylic acid, or when I oxidize a alkene or alkyne to form the diol. So any questions on that reaction scheme? As I suggest, try not to learn it all in one go. You're going to get yourself muddled up. Learn a reaction at a time. Has anybody started learning these reactions? Yes, great. Okay. So just keep on, take your time learning them so that you don't get muddled. Right, so what different ways to test yourself. Don't always try and remember A going to B. Okay? Try and work out, if I've got HBr, what sort of reactions could I make? If I've got SOCl2, what could I do? If I've got bromine, what could I do? So just think of it in terms of reagents, okay? Or I could say, I've got an alcohol. How can I form that alcohol? From what other substances can I form it from? So I could form this alcohol from an alkene or from a haloalkane. And if I use KOH aqueous, what do you think my starting material was? The alkene or the haloalkane? And I'll go up very quickly. So remember, we're forming this, and we want to, we've got an aqueous potassium hydroxide or whatever, so we either come from there or from there. So I hope you've seen where the answer is, and you can see it's from a haloalkane. That could have been a chlorine, it could have been a bromine, or anything like that. Does my Br have to be on the middle carbon, or could it have been on the end carbon? Could I put my bromine over here? Anybody want to have a go? Nope? Okay. Remember, we're replacing it. It's a substitution reaction, so we're taking one away and we're replacing it. So we've got to replace it in the same point. So if I'm adding it onto this carbon, it means something must have been removed from this carbon. Okay? Not that one or that one, otherwise the OH would have added there. So when you're trying to work backwards or forwards, always look where is that center of reactivity, because that's where the reactions happened. The OH is attached to this carbon, so my bromine or my chlorine must have been attached to that same carbon. Okay, here, what do you think my starting material is to form this amine using ammonia? If you've got, and I'll just go back quickly, if you've got your book open, you can turn to page 50, because this is where this reaction scheme is. I just lifted it straight out of the book. So if we have a look, it's again a haloalkane, okay, and treating it with concentrated conditions, okay, no water present, because then I'm going to form the alcohol. We don't want water around, so water can be there for the aqueous, but we can't have water for this one, so concentrated alcoholic. It's important that you write, even actually for achieved, that you write what the reacting conditions are. So if you just said KOH here, you probably wouldn't have got anything. But if you said aqueous KOH or KOH and water or something like that, you would have been fine. Right, HCl. Now HCl can come up in a lot of different ways. I could use it from an alcohol, but as I said, I hate using HCl from an alcohol. I always like using it from an alkene, but I don't think you'd get marked wrong with that, simply because in the standard they allow it. It's not very widely used at all, only in some reactions. And last one, I hope if you see this, you're thinking of oxidation, okay, because permanganate and dichromate, do you remember those purple solutions and those orange solutions if you've done redox? They're strong oxidizing agents, so I hope you know this is an oxidation. And what you've done is, of course, it's from an alcohol to a carboxylic acid, so you have to change this carbon over here. Do you notice the rest of the molecule stays the same? So this methyl carbon, methyl, methyl carbon, methyl stays the same, and only the carbon that's the center of the reaction has got something happening to it. Okay. Any questions on this? Do you think you would have got those? Would you have been able to work out the answer, and you're just too shy to type out the answer here? Not too sure? Okay, again, it's lots of practice, going through past papers and so on. So here's also, trying to do it in different ways. We can fill in over here. Oh, forget about the first one. That's wrong. That's wrong. You don't do this functional groups. I thought I had changed all my level 3 to level 2 problems, and I didn't. So forget about that one. let's look at this one. I've got bromomethane. Okay, I'm reacting it with ammonia, and I should have been more specific in my ammonia. I should have said concentrated ammonia. What will my product be? Does anybody want to have a go? So haloalkane with concentrated alcoholic ammonia. No. Okay, Shania is having a go. Well done. And amine, well done. Okay, and because I only had one carbon in there, I only have one carbon in the product. So, good. Okay, here I'm forming an alcohol. So, our two main ways of forming alcohols are from alkenes and haloalkanes. So, this must be one of them. So, you look at the reagent. When do we use this reagent to form an alcohol? From an alkene or from a haloalkane? Shania, well done for typing. Having a go. Okay, it's an alkene, correct. So the alkene, now remember you've got to count, you've got to look at your product and go 1, 2, 3 carbons. So I have to have 3 carbons in my starting material. Then you've got to say, right, my OH group is on the middle carbon. So my OH is going to be added on, and I'm going to also add on an H, because remember we're adding water, HOH, to the alkene. So my H is going to be adding on to the carbon with the most number of hydrogen atoms, okay, if you're doing the major product. In this compound, it doesn't matter because we've got a sort of symmetrical compound. You know, this side, we've got a methyl on this side and a methyl on that side. So if you were drawing the starting material, whether you'd drawn the double bond between these 2 carbons or between those 2 carbons, it would be correct. Because if you try to name it, I hope you can see you're going to be getting propene each time. We don't even have to put the number in. We don't even have to say 1 propene because you can't actually have 2 propene. That's an impossible name. Do you see why that's an impossible name, 2 propene? Okay. So for the rest of you, if you aren't responding and so on, you're welcome to email me later if you just too shy, because the more questions you have and get answered, the more you're going to learn. Right, and this one, I must have either clicked or I didn't animate it properly. This is a change from an alcohol. Oh, hang on, I need my reagent. That's what's missing here. I'm going from an alcohol to a haloalkane. How do I change from an alcohol to a haloalkane? And there are a number of different ways, of which one is the best way. And I can't remember which, because I did this in such a rush. SOCl2, well done. So that's the one you remember. Obviously you don't use SOCl2 when you're making a bromoalkane. If you're trying to make a bromoalkane, use HBr, because you aren't given any other variation on that. But if you're trying to make a haloalkane that has chlorine in it from an alcohol, use SOCl2. Okay, and you'll find next year you use SOCl2 a lot. In fact, you don't use any of the others. So you might as well learn it now for next year as well. Right, so the last thing that we didn't do, which I'd like to do before we then just go over a few past exam papers, is polymerization. Now, for polymerization, the main sort of questions, they ask are, if you get given this starting material, what polymer is formed, or if you get given this polymer, what was the starting material? So something similar to what we've just been doing. And then there are also the properties of the polymers. So if you've done plastics last year at level 1, you should know a lot of this, because this is actually was also done in level 1 in that standard. But if you haven't, we go over it again. So the first thing is a polymer is just a very long molecule. Now it can either be single long molecules, or they could be cross-linked with each other. So the harder they are, the more cross-linked they are. So like your car tires are polymers that are cross-linked. And by cross-linked, I mean these long chains. So you have a long chain here and another long chain, and there's a covalent bonding between them as well, just to hold it in position. It makes it much, gives it a much higher melting point. The ones that you use for your milk bottles and so on, I don't know if you've ever put a milk bottle on a hot stove by mistake or something like that, you'll know the plastic melts pretty quickly. Okay, I've done that. I don't know if any of you have done that. So, and that's because they're just incredibly long molecules, and they all get tangled up, and that's why it's a solid as well, and that helps makes it flexible, and so on. So I think that's is given in the booklet, that the toughness, because it's long and because it's tangled, there's a sort of give and take a bit, because it's not done in the crystalline ways, so it can flex all these long molecules. That's why those plastics tend to be quite flexible, and they're also quite tough. Now, if you look at this particular polymer, what functional group is there present? If we had to classify it as one of your 7, you have to know. An alkane, alkene, alkyne, haloalkane, alcohol, amine, carboxylic acid. Which one is that? An alkane. And remember what I said about an alkane. Are they reactive? Oh, that's not a very good question, actually. Nicholas, you're right. You're answering to what I wanted. I mean, they are reactive in that they burn very easily. So, you can burn plastics and so on. But they don't undergo a wide variety of reactions. It's really just breaking down in UV light. That's why plastics put in a landfill often don't decompose, because they aren't getting any light coming there to it. But if you've got plastics lying around the sunlight, they will eventually degrade over time. The other one is, of course, the burning. So if I make polymers that are just alkanes at the end, will that plastic react with anything that's inside? So if you put Coke inside or milk inside or whatever, will that plastic react with the contents? Nobody too sure? Okay, it won't, because alkanes don't react. They don't react with acids, they don't react with bases, so they're pretty stable. As I say, they only pretty much burn, or they, with sunlight and UV light, they'll break down, and particularly if there's others around, and then they'll form haloalkanes and they'll start breaking up. So if we go from an alkene to an alkane, then we form a non-reactive polymer. Next year you learn about other polymers. So this is what we call an addition polymer, because we're adding these together. Okay, each of these is what we call a monomer. Mono, one, poly, many. So we're combining lots of single units together to make a long chain. So think of it like beads on a necklace. Each individual bead doesn't do much, but if we chain them together into a very long chain, then it's got different properties. So these are like all our individual beads, and now we're chaining them up to form a long chain. So if you have a careful look at how these combine, Notice it's only the carbons of the double bonds that, that has the double bond that's combining. Because can you see those two carbons? Are these two carbons? It doesn't matter what that group is, or that group, or that group, or that group, because they're over there and they're over there. I'm just concerned with the carbons of the double bond. So what happens is this is catalyzed. It normally has something like oxygen or something like that just to get it going, to oxidize it, to start that initial bond breaking. And once that first bond is broken, this carbon now has got an unbonded, unpaired electron, and so has that one. So they're going to be very reactive now. So what they'll do is, I mean, here I've made them all happen all at once, but what will happen is one of these will break up with that catalyst, and then it's going to go hunting to try and stabilize itself. And what it'll do, it'll collide with another alkene and break that bond, and then they'll start connecting up to form this chain. So that was, say, the initial double bond. Now we've only got a single bond there. This is the new bond. That was the previous double bond. This is the new bond, previous double bond, new bond. So can you see, when you've got to draw these polymers, think of it, it's the old bond plus a new one, old one, new one. They alternate. Okay, so I was just highlighting the monomer there. If I go to the next page, if you asked what polymer would form from this compound, first of all, what is this compound? How would I name it? And I've deliberately sort of shown a trans structure to help you think of geometric isomers again. So who would like to name that? It'll be trans something or the other. Okay, nobody want to have a go? I've got how many carbons? 1, 2, 3, 4. So if I've got 4 carbons, what will my alkene be called? Meth, eth, prop, bute, pent, hex, bute. Okay, so we'll have bute. Now we know it's an alkene, so it'll end in ene. Do I have to put a number in? Can I have only one possible position for a double bond, or could butene have 2 possible positions? It can have 2 possible positions, because it could have been between the first 2, or it could be between the second and third. So I have to say where the double bond is. And so it's on the second double bond, so this would be but2ene. Okay, right. Now, if I have lots of butenes, trans butenes, and they join up, how am I going to draw it? Will it be CH, CH, CH3, CH, CH, CH3, CH? Will it be something like that? Laura, not Laura, Shania was typing, but now she's stopped. Okay, it wouldn't, and I should have actually drawn this out here so you could see. Always check to make sure that you haven't added extra bonds or so on in, because what you just do is, remember, you take your carbons with a double bond, here they are, so it's the old double bond plus the new one, the older double bond plus the new one, the old double bond plus the new one, and so on. It'll just carry on. And can you see this carbon over here is that one, this carbon over there is that one, and then we repeat. So my monomer unit is basically this grouping over here. Okay, there's another monomer unit over there, and similarly over here. So a lot of students sort of try and bring these methyl groups into the chain, but it doesn't work like that. You just look for the double bond and you just join double bonds together. So with this one, will I get a BR on every carbon, or will I get a BR on every second carbon? Every second carbon, correct. So can you see there's my unit, there it is. Okay, so there was my old double bond, here's my new bond, getting to the next one, there's my old double bond, there's my new bond, old double bond, new one. And you can see that BR is on every second carbon, because there it is on the first carbon, skip the second, then we get back to the monomer again, skip the second, we get back to the next monomer, skip the second. So do you think you can draw polymers if you're given the monomer? Good. So you just look, put the other groupings, elsewhere, just focus on the double bond. And similarly, if you get given the polymer and you're asked to draw the monomer, so if the exam gives you this, just look for the repeating pattern. And as I say, you're always going to have a double bond, then the new one, then the double bond, or the old part of the double bond. So you know that you can just split it anyway after every second carbon, because that would have to be the new bond formed to join the two double bonded carbons together. So if you just sort of split it there, and then remember the monomer always has an alkene, so then you just put the double bond in there. So you've got two bonds there, 3, 4, because that one's gone now. And you've got two bonds there, 3, 4, because that one's gone now, because we've broken those bonds. Okay, so I think the best thing is now to look at past papers, and just in the few minutes remaining, sorry. Now, if you want to look at past papers, it's 91165, and I just Google NZQA. So I really recommend you look through past papers. You just choose the standard, and I'll make this bigger so you can see what it looks like. So can you see that's the achievement standard? So if you wanted the details, this is how I started. Remember, I showed you all the reactions and whatever you had to know. It gives you the exam papers, and it gives you exemplar scripts, so you can see how a teacher has marked them, and there's comments about why they got excellence, or why they only got merit, or why they only got achieved or not achieved. And if you scroll further down, you get the assessment schedule. So you can look at the assessment schedule and go, what were they looking for merit? What were they looking for excellence? Because sometimes there's particular things they are looking for. So if you go through all the past papers and so on, you will get a good idea of what they're looking for. Right, so let's go through some exam papers, and we'll do this one, and I'll make it bigger. So this is the organic one. Notice they tend to always start with drawing some structures and naming. So with the naming, remember hyphens between letters and numbers, commas between numbers, and the only time you use a space between letters is when you're breaking from, making the break between the main stem and acid. Is this big enough to see? Can you see this? I can make it actually bigger. It may be better to see. Okay. Then also when you're naming, make sure you look for the functional group first. So it's OH. So the OH must have the lowest number. So do I start numbering from the left to right, or do I start numbering from right to left? From right to left. So this is going to end in 2-ol. I already know that because OH is an alcohol. Ol. It's on the second carbon. Then you go, I've got 1, 2, 3, 4, 5, 6 carbons. So I know it's hexane 2-ol. And I know it's hexane and not hexene 2-ol because I've only got single bonds. Okay? If I also had an alkene over there, I would also have to put that in. So it's, I doubt if you'd get that. You would get it again at level 3, but I don't think you'll get it at level 2. So we know it's going to end in hexane 2-ol, and we know we've got a side chain, because if I run my finger along here, there's no ways I can get to that methyl group without lifting my mouse or finger to get there. So whenever we've got to backtrack or lift our finger to get to the next carbon, it means it has to be a side chain. It's not part of the parent chain. And that methyl group's on the 3rd carbon, so it'll be 3-methyl hexane, no space between the methyl and hexane, so 3-methyl hexane 2-ol. Okay, do you think you could have worked that one out? Good. Okay, so I won't carry on with that. So here, now they name incorrectly. It's normally the parent chain has been numbered incorrectly or something like that. So that is, so it's a good way of checking if you've understood something. So an examiner will often ask, give you an example of something that's incorrect and ask you why. It's also to check if you've just rote learned something. Because if you just rote learn, then you won't be able to see why it's incorrect. Okay, now there'll always be something on isomers. And remember, you have to compare constitutional or structural isomers, means the same thing, with either between themselves, or you may have to compare constitutional isomers with geometric isomers, the cis and the trans type of isomers. So if you get given a molecular formula, because remember what the definition is of a constitutional isomer, or any isomer, it's where substances have the same molecular formula. Don't just say have the same formula, because that's too vague. Did you mean the same structural formula? Did you mean the same molecular formula? Did you mean the same empirical formula? There's lots of different ways we can represent chemistry. So say that it's got the same molecular formula, but the atoms are arranged differently, and so for constitutional one, the atoms are connected differently to each other. Okay, now I see time is going, so I'm not going to, because I really wanted to look at the schemes, but I'm also showing what you're possibly going to be getting. Notice how you are given a set of compounds, and you have to identify them, and you have to make a method, and notice what they give you. And that's why I was stressing the things like acids, all the reactions of acids from that you've previously learned you should be able to apply. Because I hope you realize if you get given sodium carbonate, acid plus carbonate gives salt plus water plus carbon dioxide. So if you added an aqueous solution of sodium carbonate to the substances, which one of these will react? Which one of those four? There's only one there that's an acid, the ethanoic acid. Great. Okay, well done. So, and here, that is, I hope you can recognize, is an oxidant dichromate. Okay, that orange solution, remember? So, think of what reaction have you learned that has that. Now, because you want to identify it, you must be able to say that the color changed from orange to green chromium ions. So everything you've learned in redox, you apply as well. Don't compartmentalize your chemistry. The more you connect it up, the more you'll understand it. Okay, and sorry, I'm just flipping through. And okay, here's your polymers. So do you notice what they've got here? They've got a polymer, a monomer, and you have to draw the repeating units. So like what we did just now. So am I going to get a chlorine atom on every carbon of the polymer? No, correct. Okay, what I am going to have is that every second carbon in my polymer will have 2 chlorine groups, and the other carbon in the polymer will have 2 hydrogen groups. So you just sort of draw the monomers next to each other and then just draw the line in between them, and it should then work out. Just make the bonds go straight up and down. Okay, and then notice here, this is your geometric isomerism. So I hope you know the rules for geometric isomerism. When you've got to have a double bond, a carbon-carbon double bond, but remember the 2 groups on each carbon of the double bond must be different. Whereas here I've got an H and an H, and here I've got a Cl and a Cl. So the 2 Cl's are the same and the 2 H's are the same. Notice how I give the rule and then I'm specific. So do the same thing as well with your exam. Okay, and then the sort of reaction scheme you can get, notice going, this is straightforward one to the other. Okay, but do you notice you need to know your reagents to put in there, and you need to explain using Markov-Nikov rule and or Zaitsev or something like that. They're always sort of hidden. Whenever you see mixtures or something like that, think of that. And there is an example of a reaction scheme. So they normally give you 1 or 2 substances and some reagents as well, and then you've got to work out what's formed. So an alcohol with SOCl2, I hope you realize goes to a haloalkane. Okay, where will my chlorine group be on? Which carbon? The first carbon, the second carbon. The third carbon is the same as the first one. So will my chlorine add on to the first carbon or the second carbon? The first. And we know that because my alcohol was on the first carbon. Okay. How do I go from an alcohol to an alkene? Because this is what they want here for reagent X. So remember, we need strong conditions to drag off that HOH. Okay, so you're going to be needing those hot conditions, and as I say, it's just one of the things you have to learn. It's that concentrated sulfuric acid and heated. Okay, here I hope you recognize dichromate, oxidant, bright orange, and so on. It means I've got to be oxidizing this. What is that one oxidation reaction you learnt? Well, there's 2, I suppose. But what is the oxidation reaction that's particularly oxidation only? Does anybody remember? What am I going to form for A? Not too sure? Okay, oxidize. Remember, I'm adding oxygen. So I'm going to have an alcohol with more oxygen in it. So if it's got more oxygen in it, the only thing that's got more oxygen is a carboxylic acid, because that's got 2 oxygens in it. So if I've already got 1 oxygen and I'm oxidizing it, so I'm adding more oxygen, the only choice I've got is the one with 2, and that's then propanoic acid. So that's what you would draw there. And here, if I've got a haloalkane, then with an amine, I'm going to be forming an amine on this side. So this would be propane, 1-chloropropane, and this would be propane 1-amine. Here, an alkene with a catalyst and heat. That is the reaction we did today. Okay, that, hang on. No, this one, so they would normally, it normally has a catalyst, the polymerization, but they normally also say high temperature and pressure, because polymerization needs a high pressure as well. This is the hydrogenation, and I think you can see that because it's got H2. Sorry, I didn't see that H2, I just thought of catalyst and heat. But can you see it's a hydrogenation because of the H2? So do you think you would be able to fill in a reaction scheme like that? Good. So just as I say, if you know your reactions, you'll sort of get around, I find actually the reaction scheme's the easiest part because there's very little explanation involved, and it's really just learn your reactions. And then of course you also got to identify reagent Y, which is a haloalkane to an alkene, and that was, remember, that the strong conditions again. So it's a strong base. To drag off that acidic HCl, I need a strong base. So if you sort of learn it that way, you'll remember it's an OH minus alcoholic solution. Okay. Right, and that's, then they do other, remember, observations, so colors and everything you've got to learn. I'm going to stop there because I've got something on at 12. That's the last of the organic. You're welcome to email any questions if you've got any that I can use, in the next lesson. Otherwise, I will start with the 2061 next week. There are no more Monday lessons anymore, so it's just Tuesdays. Okay. Right. You have a good day.